Hello, class. You're welcome to CHM 122 class. And as we know, CHM 122 is experimental chemistry 1. And in this course, you'll be having your practicals real time. But this is just a video to explain the general procedure for the for the experiments that we're starting with. And for CHM 122 this semester, we'll be having volumetric analysis. Volumetric analysis, volumetric method of analysis is just the same thing as titration that you are used to when you were in secondary school. And we'll be in this course, we'll be carrying out two types of volumetric methods of analysis, the acid-base titration and redox titration. For every titration, as you know, your burette is used to deliver your reactants to the flask, and you use your pipettes to take your reactant into the conical flask, and the two of them are titrated against one another. In every titration, you know the end point of the reaction by the change in the color of the reactants at the end of the titration. And that would help you to know the quantity of the reactant in the titration flask that has reacted with your titrant in the burette. And like I said earlier on, the acid-base titration and redox titrations are what we'll be looking at in this experiment. So we're starting with acid-base titration. Acid-base titration involves the neutralization between an acid and a base. And the reaction will come to an end when the correct number of moles of the base has been added to the acid at equivalence point. So you know that your base is, you add your base with the pipettes to your conical flask, and you run the acid from the burette into the base in the conical flask. So you have a precise volume of your base in the conical flask, and you run the acid into the base. And once there is a change at the end of the reaction, you know that you have come to the end point. And whenever we use an indicator, there'll be a color change when the number of moles of the acid equates the number of moles of the base. And that is when neutralization takes place in acid-base titration. In this type of titrations, we have two types of indicators. We have the methyl orange, which is for reactions that involve a strong acid and either a strong base or a weak base. And we have the use of phenolphthalein as an indicator for weak acid and strong base. When we tell you the acid and base that we are using this experiment, you yourself will be able to know the type of indicator, whether it's a methyl orange or phenolphthalein. So now the procedure for titration, for any type of titration, whether it's acid-base titration or redox titration, are almost the same. So what are the steps? The very first step is you fill your burette with the acid. And when you fill your burette with the acid, you note the reading on the burette. I will prefer you to start and fill your burette to the top, not to the brim, to where you have the mark, the very mark of the 0.00. That is the very first, that's the first calibration mark on your burette. And when you are filling it, you make sure that the lower meniscus of your content sits on that mark, the lower meniscus, and that gives you the precise volume. That is for the acid. Then you measure the required volume of the base with the pipette and transfer to the conical flask. So if the procedure tells you measure 25 ml of the base, you use 25 ml pipette. If you have to use 10 ml of the base, to measure 10 ml, you use 10 ml pipette. And as soon as you use the pipette filler, you draw the volume of the base required to fill the pipette. And similarly with the pipettes, you fill your base into the pipette to the lower meniscus. You're not filling the pipette to the brim. If you look carefully on your pipette, you see a mark. And that mark is the volume that you are to deliver. And your lower meniscus should also sit on that mark. And you transfer the contents of your pipette to the conical flask. And when you have your base in the conical flask, don't use your mouth to blow. You're going to use a pipette filler to fill, and you don't blow. You want to just release your pipette filler and you release the content in the conical flask. Don't shake, don't blow it out. That gives you the required volume. Then you add about 2 drops of your indicator to the base in the conical flask, and you mix the contents. Now, when you've added your indicator to the base in the conical flask, you place your conical flask underneath the burette that is clamped on your clamp. And for you to visibly see the color change in the conical flask, I would advise you to place a white piece of paper at the base of the conical flask on the reader stand before you start your titration. This helps you to see clearly whatever reaction is going on in your conical flask. So you hold and control the burette tap with your left hand, and at the same time, you use your right hand to swirl the contents of the flask. And you, at the end of the day, you first of all start by releasing the tap to release a drop at a time of your acid. And when you see the color change, immediately you stop, you close the tap, and that gives you a rough idea of the volume of the acids that you need to neutralize the base. So you first do your rough titration, and that gives you a rough idea. That's why it's called the rough titration. You may not get it right, but gives you a hint of the volume of the acid near volume that is required for you to have a color change. And remember, the first drop that changes the color, you turn off the tap, that gives you your end point. Don't make the color darker. Don't make the color lighter. Once the color changes and you swirl and the color change persists, sometimes when the color changes and you shake your burette, your conical flask, it disappears. But when the first permanent change in color gives you your end point. And this is how you fill your burette. When you first rinse your burette with the acid that you want to use, remember that the burette would have been washed with water, but you don't start filling again because the water there might dilute your acid. So you rinse with maybe 5 ml of your acid to be sure that there's no water left in the burette. Then when you do that, you clamp your burette and fill with the acid close to the 0 mark. You can see, and when you're filling with the burette, when you're filling your burette, you can use the funnel. But as soon as you fill to the mark, remove the funnel because there might still be some drops coming from the funnel. So you remove the funnel and take your initial reading to the 0 mark. And to avoid error due to parallax, you place your eye. So if you are short, you can climb the stool and make sure that you have your eye at the same level as the lower meniscus when taking your reading. As you can see, the person looking at the lower meniscus in the picture below. So now you also rinse your pipette first with your base, and you use the pipette filler to fill the pipette and make it to the line on the pipette. And also, like I said before, ensure that the lower meniscus sits on the line, and you transfer your liquid to the clean conical flask. Do not blow out the small amount of liquid that remains in the pipette. As soon as you release your pipette filler and everything drains out, you don't need to heat the pipette or blow it out. That gives you the accurate volume that the pipette has been calibrated to deliver. Now, we talked about the rough titration. So you record the initial reading of the acid in the burette in the table of your notebook. So like I said, you can start from 0.00. That is the very first mark on your burette. Then you add about 2 drops of indicator to the solution in the conical flask. You swirl the flask and note the color. So you have to initially know your first color before the titration starts. You place the conical flask on a white tile or a white piece of paper, and from the burette, you add a little portion of the acid at a time to the conical flask. And as you're adding it a little at a time, you'll be swirling the flask. So you have to be swirling the flask so that the acid you're adding is not just to one portion of the base, it must be to the entire mixture that the acid is reacting with. And as we're swirling and you are releasing the acid, You stop immediately, there's a color change, and you close the tap. As soon as you don't allow another drop to drop into the conical flask, then you note the final reading. The initial reading is the reading when the titration starts, and the final reading is the reading on the burette when you close the tap, and that is when you have your end point, and there is a color change as a result of the indicator added in your conical flask. So note your initial reading before titration starts, and as soon as there's a color change and you close the tap, you also note your final reading. So from your rough titration, and like I said, the first titration is a rough titration, and there you will know where approximately the color changes, and that is where your endpoint is. So at the start of the titration, you can add a large volume of the titrant, and as the color is changing, as you approach the endpoint, you begin to add your titrants in drops until the first color change occurs, and you stop the titration at the endpoint when the color changes. So this is a typical example of your table. So you know how to make your table. You have your burette reading on the first column. You have your rough titration, which is where your first one, the first titration you do, where the rough titration when you start. Then you have the first titration and the second titration. The rough titration is just to give you an idea, while your first and third titration, you are more careful as you're getting or approaching the end points to begin to release your content of your burette in drop-wise manner. And your table looks like this. You have your final burette reading first. The reason why we put the final before initial is that it will be easy for you to do a subtraction. So final burette reading, initial burette reading, volume of the acid used. So when you start, you first record your initial burette reading. And you must record to 2 decimal places. That you can see, I didn't just write 0, I wrote 0.00. And that initial reading, you put your units, and the units of measurements of volume of liquid is in that's the SI unit is in centimeter cubed. So your burette calibration is in centimeter cubed, and that is why your initial reading when you're starting will be on 0.00. Note it's 2 decimal places. Then when you run your base, your acid to your conical flask that contains your base and your indicator, as soon as there's a color change, you close the tab, and you also note the final burette reading. And let's say for my experiment, my final burette reading is 13.00. So that's, I can easily subtract my initial from my final burette reading, and that will give me the volume of my acid used. And it also remember into 2 decimal places, and that is 13.00. Now I have a rough idea that my titration would be at around 13 centimeter cubed. So it's either, if I know that, for example, my burette is 50 centimeter cubed, I don't need to fill it up again to 0 if my rough titration is far below half of the content of my burette. So now, if nothing happens, if I don't lose any acid, I look at my burette again. If it's still staying on 13.00, that will be the initial reading when I'm starting my first titration. But in case a few drops of acid were lost while you ended your first titration, you need to note, it's not, you may not meet it at 13.00. Let's say 2 or 3 drops have been lost. You may see it at 13.10 or 13.20. But assuming I didn't lose anything, I will see my initial, this now becomes my initial reading for the first titration, and I'll keep on titrating. And when I'm getting towards this 13 centimeter cube, I would close my tab and I'll record my final reading. I'll do the same thing for the second titration, record my final reading, and I will have the volume of acid used for the 3 titrations. But note that you must have an agreement between your titer values. And one thing you need to note is that you must record your work directly into your lab notes. You don't have to write it on a piece of paper and transfer. You must write it as you are doing your work, and while you are in class, effort mark will be given. Your lab notes will be endorsed by the lecturers in charge or the assistant, the person assisting the lecturer. It will endorse the lecturer will endorse your notes. So if you have written your practice, your reading on a piece of paper, you will not get any mark. So always ensure that you do your work directly. If there is a need for you to cancel, you can cancel. Nobody will penalize you for canceling. Your cancellation must just be neat, not rough. So in your lab notes, you record the volume of the acid used. So you have to state the name of the acid used. There'll be a mark for that. The base used, you have to state the name of the base. You have to state the name of the indicator that you used, and also the volume of your pipettes, because pipettes come in different volumes. So you have to state this, all these four must be reported in your notebook in addition to your table. So you have your table containing your burette readings, your rough titration, your first titration, and your second titration. And you must indicate the unit, your final reading in centimeter cube, your initial reading in centimeter cube, the volume of acid used in centimeter cube, and also state the acid used, the base used, the indicator used, and the volume of pipette that you also use. And all in taking, and at the end of your titration, you're supposed to have an average of the volume of your titer value. So in picking the values for the average titration, you can use your rough, the first and the second, provided the difference between your values is not more than 0.2 centimeter cubed. So let's look at this now. If you are going to pick an average titer value, you can't use this first and second because the difference between them is more than 0.2 cm cubed. So if I were you, I will take the rough and the second titration where the difference is just 0.1. If you use a range that is beyond 0.2, you will not get your full marks. So in calculating the average, for this particular example I have, I'll take my rough titration, which is 13 centimeter cubed, and my second titration, which is 30.10 centimeter cubed, knowing fully well that the difference is just 0.1. If I pick first and second, I will not get my mark because the difference between the first and second is 0.90 centimeter cubed. So I'll pick the rough and the second titer values, and I'll use that to determine my average. Note that the difference between your average titer values that you're going to use should not be more than 0.2 centimeter cubed. So for this week experiment, we are doing experiment 2 in your manual, and that is the titration of a strong acid against a strong base. And if you remember the indicator that we're supposed to use, where you have to use the indicator you're supposed to use, as we said before, that for strong acid and strong base, you are going to use your methyl orange for strong acid and strong base. So now you have the experiment goes as follows. The question is you have to determine the percentage of sodium carbonate in an impure sample. So you are given a sample of a base, which is sodium carbonate, and the question is you have to determine the percentage of the sodium carbonate in an impure sample. So it's assumed that the sodium carbonate you are given is not pure, and you have to determine the percentage purity of it. So in this experiment, you'll be given a solution of acid, a strong acid, and it contains 3.65 grams per dm cubed of HCl. And you have to titrate it against the sodium carbonate you are given. So we know the concentration of the acid, but we don't know the concentration of the base. And in calculating the percentage purity, we first have to calculate the concentration of the base. So what's the question? The first is you have to write a balanced chemical equation for the reaction between the acid and the base. Then from there, you calculate the molar concentration. You are given mass concentration in grams per dm cubed. So you have to calculate the concentration of your acid in moles per dm cubed. That is the molar concentration. Then the next step is to calculate the molar concentration of the sodium carbonate given. But in doing this, you know your ratio, you know your MABA over MBVB equals to NA over NB. Your MA is the molar concentration of the acid, which you can obtain from your mass concentration. VA is the volume of the acid, that is your average titer value. The MB, molar concentration of the base, you don't know. The volume of the base is the volume of your pipette. Na is the number of moles of the acid from your balanced chemical titration equation, and NB is the number of moles of your base from your balanced chemical equation. So once you do that, your CAVA, so the first one, like I said, is to calculate, I'm not going to give you the balanced chemical equation. You should be able to balance the equation between HCl and sodium carbonate. And like I said, the second step is to calculate the molar concentration. You have been given the mass concentration of your acid in grams per dm cubed. So you want to calculate the concentration in moles per dm cubed. And you know from stoichiometry, your mole concept, molarity, that is your concentration in moles per dm cubed, is equal to concentration in grams per dm cubed divided by your molar mass, which is grams per mole. I know that when grams cancels grams, you have your concentration in moles per dm cubed. So when you know your concentration in grams per dm cubed, the question is, you have 3.65 grams per dm cubed. You calculate the molar mass of your acid in grams per mole. Then that will give you your concentration in moles per dm cubed. Now, once you know the concentration of your acid in moles per dm cubed, you can now look for the concentration of your base in moles per dm cubed. Your Ca is the concentration of the acid in moles per dm cubed. Your Va is the volume of your volume of the acid, which is your average titer value. Your Na is the number of moles of your acid. Your Cb is the molar concentration of the base of your carbonate that you don't know. The Vb is your volume of your pipette of your base, and Nb is the number of moles of the base. So once you do this, of these 6 parameters, the only unknown there is your Cb, and you can calculate your Cb when you fill in all the other parameters. And once you know the concentration of your base, that is your molar concentration in moles per dm cubed. Now, the question is the percentage purity of sodium carbonate if the sample contains 12 grams of impure salt. So what you need to do is that your molar concentration of your base that you calculate, that you obtained here from this mole ratio, you convert that to concentration in grams per dm cubed. Since the question gave us the mass concentration of the impure salt in grams per dm cubed, so the moles per dm cubed that you obtained before, you convert it to grams per dm cubed by multiplying by the molar mass of sodium carbonate. So you have to multiply your moles per dm cubed that you obtained for the base by the molar mass of your base, which is your sodium carbonate. That will give you the concentration in grams per dm cubed. And once you know the concentration of your pure substance in grams per dm cubed, you divide it by that of the impure substance, which is 12 grams per dm cubed, and multiply by 100, and that will give you the percentage purity. And that is the first experiment we are going to do. Now let's move to the second experiment. The second experiment is the redox titration. So the redox titration is a titration that involves oxidation and reduction reactions. Redox, from the name, is reduction and oxidation reactions. This titration also is similar to acid-base titration. The same way you fill your burette and you run your content in your burette to the conical flask and you get your endpoints. But the difference in this now is that instead of balancing our equations like the acid-base, balancing the number of moles of your reactant, we balance the equation electronically. You identify which species is being oxidized, you identify the species that is reduced, and you balance the electrons the number of electrons, and the number of moles of your reactant. So in this experiment, will be the oxidizing agent that we'll be using is KMnO4. And why is KMnO4 an oxidizing agent? You will see later on that the oxidizing agent usually is what is reduced. If you look at KMnO4, the oxidation state of oxygen there, of manganese here is +7, and it's going to get reduced to +2. And when it is reduced, that means that it is the oxidizing agent. So in this case, the solution we are using, potassium tetraoxomanganate 7, KMnO4, the oxidation state of manganese is reduced from 7 +7 to MnO2, which is 2+ in an acidic environment. So before the titration, a known quantity of acid is added to the solution, as you see later on. In this experiment involving KMnO4, when it is used for redox titration, the KMnO4 itself is self-indicating. What we mean by this is that the KMnO4, you don't need to add any indicator. You are not adding any indicator to the content in your conical flask. So the color will change by the end of the reaction between the oxidizing agent and the reducing agent. So the endpoint is detected when the colorless solution in the conical flask turns from pop to light pink. And how this occurs is that 1 drop of your KMnO4 is added to the equivalent amount of the titrant and will give you a color change. So when you are doing this titration, you make sure that you don't splatter your KMnO4 on the sides of the conical flask. You add your KMnO4 is in your burette, and your reactant will be in your conical flask. So you are going to add it drop-wise. And as you are adding, you'll be seeing that the color will be changing until you have a permanent color change. So the experiments we are doing today is the reaction between a metal, you have to determine the atomic mass of metal M in an oxalate given your against potassium tetraoxomanganate 7, and this KMnO4 contains 3 grams per dm cubed of the solution, and you are given your metallic oxalate containing 14.0 grams of the salt. Your oxalate has this formula COOM2. Your M here is what you are looking for. The metal is the M that you are looking for. So you are titrating a metallic oxalate against KMnO4. So your metallic oxalate M2C2O4, which is the same thing as COOM bracket 2, is a reducing agent. So your reducing agent, so the oxalate ion can be oxidized to carbon dioxide. So this is the oxalate ion, C2O42-. Remember, your M here is the metal. So this is the ionic form of the oxalate ion. And when it is oxidized from this to CO2. And if you look at, if it gets oxidized, 2 electrons has been lost. Then the oxidation of the oxalate ion is shown by the increase in the oxidation state of carbon. The oxidation state of carbon is increased, and that is why it is oxidizing. That's the oxidation half equation. Then your KMnO4 is reduced, as we said before. That is why it's an oxidizing agent. KMnO4, the ionic equation MnO4- will get reduced to Mn2+. So you have to balance the number of electrons and the number of hydrogen ions. So when you balance the equation, you have a balanced ionic equation from your oxidation half equation and your reduction half equation. You merge the two together to get your overall equation. So what is the procedure? You prepared 10 cm³ of your oxalate solution in your conical flask. So you use your pipette and take 10 ml of oxalate solution, and you are going to be provided with 2 molar sulfuric acid. You have to be very careful, it's conch acid. And the reason why we have to do this is that the reaction can only take place in an acidic medium. So your conical flask, when you prepare your oxalate solution, you add 10 cm cubed of your sulfuric acid, equal volume, and you heat it slightly. You're not boiling. You're going to heat it slightly to about 60 or 65 degrees. And when you bring it down, you titrate it against your KMNO4. So the KMNO4 is in your burette. Remember, you prepare your oxalate solution into your conical flask and add 10 cm cubed of your 2 molar sulfuric acid, which you will heat before you start your titration. So you are going to introduce the KMNO4 slowly from your puree. Your KMNO4 is purple, so you have to be very careful to note the volume because your burette will be darkened. So quickly, maybe you can put the touch of your phone to be able to see the reading on your burette. You are going to fill it also to 0, and you begin to introduce your KMNO4 from the burette slowly so that the pink color will be discharged as you're adding your KMNO4. And as you're dropping the KMNO4 into your solution, it will be clear. You won't see anything until you have a very faint pink color. Once you see, you shake your conical flask and you have a color that is pink, you close your tap, and that is your rough titration. And you do 2 or more titrations to get your first, second, and third titration. And remember, the difference between them should not be more than 0.20 cm cubed. And that is when you record all the values on the table like we had before. Volume of the code. So you have your burette reading for the volume of the KMNO4, the final volume of KMNO4, the initial volume of KMNO4, and the volume of KMNO4 used. And when you do it repeatedly, you now find your average titer value. And like I mentioned before, your average titer value should not be different should not differ more than 0.20 cm cubed. Now to your questions, write your half equations, the oxidation half equation for your oxalates, the reduction half equation for your KMNO4. Then you now balance the overall reaction for the redox titration. Now, the first thing is that you convert the molarity of the oxalate. You are given your oxalate in grams per your KMNO4 in grams per dm cubed. You convert it to moles per dm cubed like we did before. And that is, you divide your concentration in grams per dm cubed by the molar mass of your KMNO4. That will give you your molar concentration in moles per dm cubed. Then you now use this relationship, your concentration of the oxidizing agent multiplied by the volume of the oxidizing agent divided by the concentration of the reducing agent multiplied by the volume of the reducing agent. And you divide the number of moles of the oxidizing agent by the number of moles of the reducing agent. Here you're not going to, some of you are putting CAVA, CBVP, you're not using acid and base, you are using oxidizing agents and reducing agents. Our oxidizing agent is your KMNO4, your reducing agent is your oxalate. And when you do this, you know the concentration of your oxidizing agent, which is what you have calculated here in moles per dm cubed. You know the volume of your oxidizing agent, that is the volume in your average titer value. The number of moles of your oxidizing agent is the number of moles of your KMNO4 after you have done your overall redox equation and you have balanced it, the number of moles of your KMNO4. Then the concentration of your reducing agent, that is your oxalate, that is what you don't know. The volume of your reducing agent is the 10 ml that you have added, that you have pipetted, is the 10 ml. You are not putting the volume of your acid, only the volume of your reducing agent, and number of moles of the reducing agent is there. Then when you do this, the unknown is, you'll be able to find your unknown in moles per dm cubed. And now you calculate the molar mass of the oxalate from the concentration you have in moles per dm cubed. So once you know the concentration in moles per dm cubed, the question has already given you the concentration in mass per dm cubed. You have been given the concentration of the oxalate in mass per dm cubed, and you have also been able to work out the concentration here in moles per dm cubed. You can easily find the molar mass in grams per mole. Once you know the molar mass in grams per mole, let's call the molar mass kilograms per mole. So the molar mass of this oxalate M2C2O4 is kilograms, which you are going to get from your molar concentration and your mass concentration. And once you know this, you can easily find your M, which is the atomic mass of your metal. And that is the end of the experiments. Thank you very much.